Hello there, this is lesson number 7, and it's on a topic called fundamental interactions. Okay, so we've already come across the word fundamental. We know that is about matter particles like quarks. Quarks is a group of fundamental matter particles. Leptons is another group of similar but different fundamental particles. Now we're going to have a look at this thing called fundamental interactions. And what that really means is what is it that holds all of these particles we've got, all these quarks and leptons, what is it that holds them all together and makes up things like protons? Fundamental interactions could be renamed as fundamental forces. And just like you can take quarks, you can take two up quarks and a down quark and put them together to make a proton, for instance. We have these four fundamental forces, and it's possible to combine some of them together. But this is ongoing physics, and we don't have a complete picture of what's going on. Now, the four fundamental forces are the gravitational force, and I could also use the word interaction here. Every time I use the word force, I could use the word interaction, or I could do vice versa. The second one is the electromagnetic force. Now, you'll have heard of these before. Gravitational force, obviously, that's what keeps the Earth orbiting the sun. That's what makes apples fall off trees and hit the ground. Electromagnetic force, I've come across this a couple of times with things like particles that repel each other. Two negative particles will repel each other because of the electromagnetic force. And you've also come across electromagnetic in the electromagnetic spectrum of all the different types of waves that are slightly different with different wavelengths. Here's two new ones. The weak force and, very aptly named, the strong force. So what we're going to do is we're going to look at what is it that causes these forces, how strong are they in comparison to each other, what sort of range do they work over. So range, their strength, and the cause of the force. And again, this is all just words that you've got to learn. There are no calculations, or if there are, they're very, very few. I'll need to go back through all the exam questions on this standard model to see if there are actually any calculations, but it's all stuff that you need to get written down. You need to learn it, and they're written answer questions generally in exam papers. Right, so I mentioned that some of these are fundamental forces. Some of them can be combined. The electromagnetic force and the weak force can actually be combined to make something called the electroweak forces. So you can build up other composite forces by looking at a combination of them. And this is one of the things that physics is trying to do. We're not anywhere near doing this yet. Is trying to get some sort of what's called unifying system where you can combine these. And what does it actually mean if you combine some of these? So two of them can be combined to make another one. It's like three quarks up, up, and down. They're fundamental particles. They can be combined to make a composite particle called the proton. The electromagnetic force and the weak force can be combined to make this thing called the electroweak force. So an attempt or attempts are ongoing. And I think that's the sort of holy grail of physics. Right. Okay. Hopefully you're writing this down. Again, you ought to be able to pause the video. And if that doesn't work too well for you, try downloading it and pausing it. And then you'll be able to make your own notes as you go along. There will be an assignment yet again, because there are no calculations. There will be some writing to be done. There may be some questions that come together in your assignment. So this is obviously in a video in an announcement, and an assignment to handwork in a couple of days later will come along as well. Okay, so what is it that forces do? Now, firstly, forces can work at a distance. And the most obvious one of these is the gravitational force, where we've got the sun and we've got the earth, not to scale, and they're bound together by gravity. Why doesn't Earth actually fall into the sun? Because it's in an orbit, it's going round and round and round. And if you're orbiting, you're held in towards the sun. If you turned off the force between the sun and Earth, if you switched off gravity, then Earth, instead of carrying on in an orbit, Earth would just go flying off in a straight line. So we can get, of the four forces, we can get three of them into the standard model. So the standard model is not a complete picture of what's going on. We don't know if we're going to be able to get the last force, which is gravity, actually. We don't know if we're going to be able to get gravity fully into the standard model, because there's still physics we don't understand. So we can very easily, I say easily, you need to be a particle physicist, you need to have access to multi-million or billion-pound accelerators to do this, but we can get the idea that three of the forces, and that's the electromagnetic force, the weak force, and the strong force, we can get three of them into the standard model. We ought to be able to get gravity into it, but we can't get that to fit just at the moment. And I'll be speaking about that later in this lesson, about how we get gravity into the standard model. Now, what you need to remember, I think, is the standard model is actually a model that consists of particles. And what may be surprising is that we can describe these forces in terms of particles. And again, that will come up in this lesson. But before we get onto that bit, let's have a look at the strength and range of our four forces. Okay, so I'm going to do a little bit of explanation, which you'll need to write down, and then finally we'll stick everything into some sort of table where you can compare them. So let's have a look at what exactly are these forces, what do they do, where do they operate, how strong are they, and what's their range. So let's start with the gravitational force again. Now, the gravitational force, as we have already said, acts on masses. and that's like masses that we can actually see and explain, things like the sun and the earth, apples falling off trees and hitting the earth. It's in fact the weakest of all the four forces. But conversely, it has the largest range. Now, when I say it has the largest range, gravity can work over hundreds of thousands of light years. It's gravity that holds together our Milky Way galaxy, which is about 100,000 years across. Plus, there are other satellite galaxies. We've got the Andromeda galaxy. We've got things called the Magellanic clouds discovered by a Portuguese sailor called Magellan. You can't see the Magellanic clouds from the northern hemisphere. You need to go down below the equator. But all of these things like the Milky Way galaxy, Andromeda galaxy, Magellanic clouds that crop up in astrophysics are all actually held together over huge, huge distances. And so it's fair to say that the gravitational force has an infinite range. It gets weaker and weaker as you get further away. But if the masses are enormous, like the mass of a galaxy, then it's quite easy to see how the masses can be attracted towards each other. And you need to refer back to our dynamic universe if you want to look at that. So that's the first one, gravitational force. Let's move on down the list that we had before. The next one is the electromagnetic force. And what this does is it affects all electrically charged particles. So, for instance, two negative electrons they're going to get repelled, they're going to get pushed apart, and it's the electromagnetic force that's responsible for pushing two electrons apart. It's also the force that's responsible for attracting an electron to a proton, for instance. And again, it's a bit like the solar system. The electrons are orbiting round and round and round. And they're subject to a force. They don't actually fall in, they don't come any closer, but the electrons are orbiting around the proton, and that again is the electromagnetic force that holds electrons orbiting around protons. The electromagnetic force also can be used to explain how magnetism works, how magnetism works. So two north poles of a magnet will repel. A north pole and a south pole will attract each other. And the last thing that electromagnetic forces explains is the behavior of light and the other waves that are in the electromagnetic spectrum. So that's the second one. Now, electromagnetic force is stronger than gravity, and it also has an infinite range, though there becomes a distance where things are so far apart it doesn't really affect things. The gravity force, but also has a very, very large range. Okay, so that's the second one of our four fundamental forces. What are they? What do they do? How strong are they? What's their range? Now, the third one is the weak force. What does it do? How big is it? What's its range like? And it works on quarks and leptons. So when you understand that it works on quarks and leptons, you can see that its range is quite small because quarks are very closely packed together inside a proton, leptons also. Okay, so it's responsible. What's the weak force responsible for? What does it do? It's responsible for beta decay. And you know what that is, that when a neutron turns into a proton, the proton stays in a nucleus and the beta particle is emitted along with a neutrino. And we've talked about that before. So beta decay doesn't just involve an electron being ejected, it also is responsible for neutrino production. So I'm going to say beta decay and neutrinos. Any interaction that produces neutrinos is subject to the weak force. Why is it called a weak force? Because it's much weaker than the electromagnetic force, and it only works over a short distance. And I will put all of these distances and strengths in a table after this, so you can have a look and see how they compare. So that's the weak force. We've got one more. We've got the strong force. Now, the strong force, it's very aptly named because it is the strongest of all the forces. What does it do? It also acts on quarks, and it's actually the force that holds quarks together. Now, where are the quarks? Well, we know that you have three quarks, two ups and a down, inside a proton, and it's the strong force that holds these quarks together in the inside. Now, I drew earlier in another lesson, I drew a proton, and I put an up and another up, and I put a down inside our proton, and I drew some squiggly lines, and it's these squiggly lines that is the strong force that I drew before. So this is a representation of a proton, which is a composite particle made of three fundamental particles held together by a fundamental force called the strong force. What else does it do? Well, it obviously holds together two quarks in the meson as well, plus any of these other exotic particles. But just think of it as it's responsible for holding the quarks together. Now, not only does it hold the quarks together inside a proton, so I've got up, up, down, and I can have another proton, up, up, down. I will put the downs as red things, and I've got two neutrons, for instance, and 2 neutrons. A neutron is a down and a down and an up. And another neutron would also be a down and a down and an up. Okay, so forget about the neutrons really, but the protons are both positively charged. Got a big positive charge. Should only be one positive really, not two, because it's a +1 charge, and that's a +1 charge. In fact, I'll get rid of one of them. So I've got a plus charge on my proton and a plus charge on my proton and 0 charge on my neutron. Now these two should force the 2 protons apart, but they don't get forced apart. They're actually held together with the strong force. You'd think that perhaps the electromagnetic force acting between 2 particles would force them apart. Well, 2 protons inside a nucleus don't get forced apart. They're held together by the strong force. The strong force must be pretty strong to overcome the electromagnetic force. And indeed, it is strong, and it is the strongest of the 4 forces. So the strong force is working in 2 areas. One is to hold the quarks together inside a proton, and the other thing it's doing is it's actually holding all the protons and neutrons together inside the nucleus. So it's a pretty interesting force that you've got. Some of it is being used here, and some of it is being used here, and sometimes the bit that's being used here is called the residual strong force, because we start off at the fundamental level with quarks being held together, and there is some strong force left over called the residual strong force that holds each of the protons and neutrons together inside the nucleus. So the strong force holds quarks together, holds protons and neutrons together. Now, because this is a proton and these are protons and they're in the nucleus, sometimes this strong force is called the nuclear force because it acts within and around the nucleus. Okay, so if the strong force didn't exist, 2 protons would fly off. So it's got to hold them together, and it's got to hold the quarks together. Okay, so what we want to do now, we've got an idea of what the 4 forces are, what they actually do, how far do they operate, what's their range, and how strong are they? And I want to put that together in a sort of comparative table that looks at their strength and range. Okay, so I'm going to start with the name of the force. This is in my table. I should be drawing some lines, but I'll probably draw the lines afterwards to make up my table. I've got the strong force. I've got the electromagnetic force. I'm not going to keep writing force. I've got the weak force. And I've got the gravitational force, or the strong force, or the strong interaction. Doesn't really matter. Okay, I want to look at their relative strengths rather than actually giving a number or unit to the strength. I'm going to look at relative strengths. Now, we've looked at things like relative charges before. We ought to know that a proton has a relative charge of +1. Its actual charge is +1.6 times 10 to the -19 coulombs, but we're going to call that +1. In the same way that we could take 2/3 of that and say that's the relative strength, if you like, of an up quark, and we could take 1/3 of it and say that's the relative strength of a down quark. So we're going to use numbers like +1, for instance, and then we're going to compare the relative strengths with each other rather than actually giving real numbers to them. So the strong force is the strongest, and we'll just call it strength 1. And then the electromagnetic force is 3 orders of magnitude less, 10⁻³ . The weak force, weaker still, as its name might imply, 10⁻XVI. And the gravitational force, the weakest one of the lot, 41 orders of magnitude less than the strong force. So the strong force is incredibly strong, has an incredibly short range. And my last column is going to be about the range. Now, I'm actually going to use units here for the range, and the units I'm going to use are units like this. Now, FM stands for femtometers. Now, femto is just another prefix. We've got prefixes like milli. We've got kilo to make it bigger, milli to make it smaller. We've got micro, we've got nano, we've got pico. We've got a new one now called femto, and femto means 1 × 10⁻15 of a meter. So an FM, femtometer, 1 × 10⁻15 of a meter, an incredibly small distance. And the range is going to be measured in femtometers, and the strong force has a range of 2 femtometers. In other words, 2 × 10⁻15 meters. The electromagnetic force, we said it's huge, and in fact it's got an infinite range, and there is a symbol for an infinite, and it's the infinity symbol, an 8 on its side. We've got the weak force, and again the weak force is a force that acts inside the nucleus, and it's much, much weaker than the strong force, and it's 10⁻³. And the gravitational force, again, we've said it's huge, goes over light years, so once again we're going to call it infinite, and we're going to put the infinite symbol there at the side so you know that it's infinite. Right, okay, so that gives you an idea of the strength and the range. I should be nice and neat now and complete my table with some lines, and you might want to do that in your notes with a ruler, so it actually looks like a table. Okay, moving on. Now, what is it that makes up these forces? We've got some names, we've got an idea of how strong they are, how far they work over, but what is it that makes up these forces, and how does that fit into the standard model? Now, the standard model is a model of fundamental particles. And this whole unit, or this whole subsection, is called the standard model. And really it's an idea of all the different particles that go to make up stuff being matter. So it's particles, and then you're going to go, okay, right, so forces, how do forces fit in to the standard model of matter particles? How does that actually work? So physicists believe that these forces are actually caused by particles, and they're how they move about and what they do. So the forces are caused by, the four forces are caused by what are called either, and it's the same thing, carrier particles, or, and I've got to look this up because I can't remember the exact wording, force mediating. Now, these are just words. And again, you've got to learn these words. So if you see these words coming up in exam papers or question papers, you'll know what they're talking about. So the four forces are caused by particles. And they are called either carrier particles or force mediating particles, mean the same thing. Now, how does that work? Well, if we look at the electromagnetic force and we look at two electrons, we know that two electrons are going to repel each other. Now, how do they repel each other? Well, you could say that they repel each other because there's some invisible force that's between them that forces them apart. But physicists think that this invisible force is actually made up of these things called carrier particles or force mediating particles. Now, that shouldn't sound, it might sound a bit weird, but if you think about it, if you think of force being a sort of energy field, if you like, then perhaps it's not a far step to realize that E equals mc squared, that these forces, this invisible energy stuff, can be translated into some sort of mass, into some sort of particle, into stuff. Now, the way I want to do this and look at particles is by way of what's called an analogy. Now, an analogy is a common everyday thing that we're happy with that might explain how forces work by carrier particles moving between two things. So this will go some way, it's not perfect, but it will go some way to making you have some sort of understanding of how particles can cause forces. And what I want to do is I want to have two ice skaters, and the two ice skaters are facing each other and they're standing on some ice. And I've got skater A and I've got skater B, and skater A has a very heavy ball. Imagine a basketball filled with sand. Now, I don't know whether they still have these down in the P department, but there used to be things called medicine balls, and they're about the same size as a basketball, and they're filled with sand, and they're really heavy, and they're used for doing exercises with picking them up and moving them around. So what I want you to imagine is that skater A is holding one of these large balls, one of these large medicine balls. And skater A throws the ball towards skater B. Now, if you can imagine that they're standing on ice, you could imagine this happening. It doesn't even have to be ice skaters. We've got a lot of icing weather at the moment. If you're standing on some ice and you threw a really heavy object towards another person, then skater A would go that way, would go backwards. And that's just like a conservation of momentum thing. If you throw an object there, an explosion here, throw an object there, then this person's going to go backwards. When person B catches that ball, when it's gone across the distance, person B is also going to go that way. So I want you to think of something like the electromagnetic force of two electrons is actually caused by a particle being thrown from one electron to the other and then possibly being thrown back again. And that would cause the people to get further and further and further apart. So the forces are caused by the transfer of particles. These particles are carried between two people or two particles, and they're called carrier particles or force mediating particles. Okay, so each of the four forces that we've looked at, gravitational, electromagnetic, weak and strong force are all caused by particles being exchanged backwards and forwards between two things. And I want to look at and name what the particles are called. Rather than just saying there is an electromagnetic force, the electromagnetic force is caused by a particle being transferred from one place to another. Now, I did say this is an analogy. It's a really difficult analogy to imagine that you can throw something from one person which actually attracts two things together. But I want you to just bear in mind that all analogies aren't always perfect. Okay, so I'm going to start with the electromagnetic force, and there's a reason why I'm starting with the electromagnetic force and not the gravitational force this time, as will become clear shortly. So I've got the electromagnetic force. And what is it? What is the carrier particle, or what is the force mediating particle that gets thrown backwards and forwards? Now we have a name for the group of particle that does this, and it doesn't matter whether it's the electromagnetic force or the weak force or the strong force or the gravitational force. There is a particle, a group name for the particle, and the group name is called a boson. Bose, B-O-S-E, was an Indian scientist. That's an S there, by the way, B-O-S-O-N, named after an Indian particle physicist called Bose. Can't even spell Bose now, B-O-S-E. And if you're familiar with really expensive headphones and loudspeakers, also invented by another person called Bose. I don't think they were relatives. So we stick together these forces in a group. We stick together things like ups and downs together in a group called quarks. We stick electrons and neutrinos in a group called leptons, and we're going to stick these carrier particles in a group called bosons. So the boson that is responsible, or the force mediating particle that's responsible, that's passed backwards and forwards between two things, is a word you've come across before, and it's called the photon. It has a symbol and it has zero mass. Or if it does have a mass, it's pretty small. We're not necessarily certain. This is another one of these things that we don't know about particularly. So what is it that's transferred backwards and forwards between two repelling electrons? It's a photon that zips between the two, and the photon causes the electrons to repel each other. So the photon is a boson. Right, so that's the electromagnetic force. Weak force. Now the weak force doesn't have one boson, it has three bosons that do the job. Three different force mediating particles, and they're called the intermediate vector bosons, and there's three of them, and their symbols are W plus, and the second one's W minus, and the third one is Z, and this Z sometimes has a naught up next to it. So there are three different bosons that do the weak force, that cause the weak force, that get thrown backwards and forwards. Now they're more massive than the photon. If we think the photon has got a tiny, 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 tiny mass, almost nothing, the mass of the intermediate vector bosons responsible for the weak force is about 10 to the power of 5 times the mass of a photon. So I'm not going to write the names here, but the names are W plus, W minus, and Z. Just call it Z. Those are the names, and those are the symbols. So you just have to say, right, what is it? Well, you wouldn't write out W plus, you just write W with a plus sign like that. You can write out photon, write out the word photon, but there is no word for W plus, nor W minus, nor the Z boson. Okay, move on. Strong force. Now, the boson responsible for the strong force does have a name you can write down. It's very aptly named. It's called the gluon, named after glue that holds things together, sticks things together. So the gluon is sticking together quarks inside a proton or a neutron, and it's also this residual strong force that's left over that's responsible for holding protons together in the nucleus. So it's called the gluon. It's got a symbol which is like a sort of G. It's more like a sort of G with a curly tail. And I ought to know what its mass is, but I've just left that out. I might have to come back to that one in a minute. Lastly, the gravitational force. Now, this is where the standard model goes a bit wonky, because we've got evidence that all of these bosons exist. We can do experiments, physicists can do experiments in particle colliders and accelerators, and they can come up with a theory, and then the theory is borne out by some experimentation. And the theory of the experimentation matches up quite well between the theory and the experiment for electromagnetic force, weak force, and strong force, but there is no experimental evidence for the boson that causes the gravitational force. Now, the boson that causes the gravitational force is something called the graviton. So it exists in theory because we know that gravity should be one of the fundamental forces, but it doesn't quite fit in. And it may be that it never fits in which case future physicists are going to have to rewrite the standard model of fundamental forces. Or it could be that we've just not discovered the particle that actually causes the graviton, or makes up the graviton. Its symbol is G with a little naught. I'm just going to go back and see if I can find out some stuff about the masses. So we think that a photon has zero mass. We think that a gluon probably has zero mass, but we're not certain because we haven't actually been able to measure the mass yet. That's another thing for particle physicists to do. We can show that it exists, but we can't actually measure its mass. And the graviton, what's its mass? It also has zero mass. So there are massless particles, if you can imagine such a thing, massless particles for three of them, and a particle that actually has a mass that you can measure in a particle accelerator as shown by some sort of energy. And that is the four fundamental forces. Okay, so three of them fit very well into the standard model. Got lots of evidence for them. Gravitational force, not so much evidence. Now, there is one other boson that you may have heard of, and it was discovered not too many years ago. It's called the Higgs boson. First, it was thought of in theory by a physicist called Peter Higgs, who's from Edinburgh. So it's a bit of Scottish physics, which is why I'm just throwing it in. Peter Higgs from Edinburgh came up with a theory back in the 60s that there was another boson that exists, a particle that exists that's responsible for giving things mass. And the discovery of it in terms of practical work was carried out at CERN. And I think it was only about 6 or 7 years ago that CERN announced that they had discovered the Higgs boson in an experiment that exactly matched Peter Higgs's theory that he did all those years ago. But the Higgs boson isn't in higher. Higher physics, the syllabus was written before the Higgs was discovered, and they've decided not to rewrite the syllabus. So you may have heard of the Higgs boson, but it shouldn't come up really in any questions. Okay, if you wanted to, you could make up a table. I'm not going to do it this time, but you could make up a table with the name, the symbol, and its mass, should you wanted to. For each of these, you'd have photon, this gamma naught, photon, symbol, zero mass. You'd have the name, intermediate vector boson, symbols, those three symbols, and in the last column you'd have how much mass it has, a lot of mass, strong force 1 2 3, and the graviton 1 2 3. You can make up a table if you wanted, and I'll leave you to do that if you want, because that's the end of this lesson. Thank you very much. That was, I believe, lesson 7.